This is CPE 133. This is Chapter 12 in the Free-Range Verilog Foundation Modeling text, and we are here to talk about simple registers and also inline registers. And so there's the disclaimer. You're not going to learn this by watching boring videos or reading the text. You actually need to break down and generate some circuits. Do some real modeling with Verilog. This is going to be a relatively short video because registers are very similar to D flip-flops. In fact, everyone considers registers as a kind of a multi-bit or an n-bit D flip-flop. Registers are super popular in digital design. They are, of course, they have memory, of course, but also there's a whole bunch of different types of registers out there. We're going to talk about simple registers in this chapter, and then we're going to finish this set of lectures off with counters and shift registers. So this is our basic register model here. And the idea here is you got input data and output data, and that input data is going to be latched into this register. So typically we have a control input there, which is the load control. Often we just call it LD. So essentially that governs when the data in will become latched into this register. So the notion is load signal or the loading action is typically always synchronized with the active clock edge. So this is a clear signal. Many registers have clear signals. It's very easy to design the clear signal as either synchronous or asynchronous, but typically the load signal is a synchronous signal. So jumping right into it, so what we want to do is model this simple n-bit register. Is not enough to say, hey, just model it. We've got to say some stuff. The clear signal, by looking at this, you don't know whether it's synchronous or asynchronous, but the problem calls out asynchronous. And also these register circuits that we're going to get into, even this one has multiple control signals, and we have to declare or state the precedence that these signals have. So essentially in this, what we're saying here is the clear signal has precedence over the load signal. You gotta say that. If you didn't say that, you wouldn't really know how to model this correctly. And so this is our solution. The idea here is it is generic. There's our parameter. We've seen this many times before. The idea is parameters uses a default value, but you can change it when you instantiate this module. Another notion here is it is active to the always block here is active to the positive edge of a clear signal. Essentially, when one of these two signals, one of these two events here is going to cause this always block to fire off, and when it does, it's going to evaluate this if statement. So the first thing it sees in the if statement is if clear equals 1, and so that's going to be essentially that's going to be a rising edge. So when there's a rising edge on this signal, that the state of that signal is going to be 1, and under those conditions right here, the flip-flop or the register here is going to clear. So if this doesn't test as true, then it's essentially the notion is it's going to check the state of the load signal. So if the load signal is asserted, it's actually going to do the loading in this. And so that's the whole circuit here. We modeled this without an else statement. The fact that we use these pause edges here cause the data out to be registered. We could have put an else in there, but I think it looks better without an else. Anytime I see an else, I think it's a catch-all, and it makes me nervous. But this works. It's all fine. So this is the exact same problem, and the difference is the clear signal is synchronous. I just want to emphasize the fact that when you're doing these problems, you can design any register you want starting from just this basic n-bit simple register. And so the idea here is what I want to do is make the clear synchronous rather than asynchronous, and the only change I'm going to make is I'm going to scribble out this right here. Essentially, by scribbling that out, the always block is now not sensitive to the clear signal. It's only sensitive to positive edge on that positive edge of the clock here. If first thing it checks is the clear signal to see if it's asserted. If it's not asserted, then it goes on to check the load signal. So once again, really straightforward to take these basic models and change it to whatever you need to be working with. We're working with Verilog, and there's the notion of registers and reg type variables. Okay, so the notion here is very confusing. Reg type variables was an unfortunate name. It is something that was changed in System Verilog to logic types, but you know, I still prefer working with Verilog here. So registers themselves are multi-bit storage elements, but when I declare a reg type, it doesn't necessarily mean it's a register. Whether it's a register or not, or better way to put it, whether it has the ability to store data or not, is based on how I use that register. So typical use of reg types here, we've seen these in the module interface and as internal interfaces, but also we're going to see the next example that you can actually use these as registers within a given module. So this is a code fragment, and I call these inline registers. I don't know if that's I borrowed the term from C++. I honestly haven't ever seen it mentioned in the context of Verilog, so you got to be careful with that. But essentially what it means is that we have these modules that were registers, but we can also use an internal signal to induce a register also. So here is my internal signal. It's declared as a register. The outside world doesn't know about this signal, based on the part of the module you don't see here. But all I have to do is take that same always block and drop it in my code somewhere. And once I do that, here's the pos edge. It causes this anything assigned inside this always block, which is essentially R data, to be a register. So R data is going to be a register. So I know it's going to be a register. Typically, that's why I like putting an R underscore in front of it to kind of sort of self-comment it and to remind the world that it is a register. Because remember, anytime you use a reg inside a module like this, it doesn't necessarily make it a register. Whether it's a register or not depends on how I set up the code. So this code is set up for R data to be a register, and I call them inline registers. Very, very, very useful in Verilog. That's why I toss it out there. Oftentimes you just need a register somewhere in your design, and you don't really want to go through the rigmarole to instantiate a register. This is a chapter on registers. They're sequential, typically speaking, sequential synchronous storage elements. Oftentimes we think of them as n-bit flip-flops, as essentially like n d flip-flops all connected in parallel. So the several type of registers out there. We only looked at simple registers in this chapter. We'll be getting into counters and shift registers next. And we also took a look at this inline register, which gives us the ability to take an internal signal and induce a register on it.